ChatGPT has taken the field of NLP by storm with its amazing ability to generate content, code, have interesting conversations, and more. This is a state-of-the-art LLM developed by OpenAI. The GPT in ChatGPT stands for Generative Pre-trained Transformer. Let's break down what we mean by this. We say the model is generative because it can generate human-like text. Given a prompt or context, ChatGPT can continue the text in a coherent and contextually appropriate manner. This makes it really useful for tasks like text completion, dialogue generation, and content creation. The pre-trained aspect of GPT is crucial. Before fine-tuning for specific tasks, GPT undergoes a pre-training phase where it learns from massive amounts of text data. This process equips the model with a deep understanding of language, grammar, and a broad vocabulary. And of course, the transformer in the name is a reference to the transformer architecture we discussed in the last section of this course. There have been several iterations of different GPT models, so let's take a look at how this LLM has developed over the years. The development of ChatGPT represents a remarkable journey in the evolution of large language models, marked by a substantial increase in scale, performance, and applicability. Let's explore how we got here. The first GPT model, GPT-1, emerged in 2018 as a product of OpenAI's efforts to build a general-purpose text generation model. GPT-1 was trained on a modest dataset of 40 gigabytes of text from the internet, comprising of a wide variety of sources. It had 117 million parameters, making it one of the largest language models at the time. GPT-1 demonstrated its capabilities in text completion and generation tasks, but had limitations in understanding context and producing coherent long-form text. GPT-2 was released in 2019, and it was a watershed moment. It featured a significant increase in scale with a staggering 1.5 billion parameters. GPT-2, trained on more extensive and diverse data, demonstrated remarkable advancements in generating coherent and contextually relevant text. In 2020, we got to GPT-3. This had 175 billion parameters and was trained over a vast data set encompassing a significant proportion of the internet. Few-shot learning capabilities were also developed with this model. By 2022, we were at GPT 3.5, and now in 2023, we have GPT-4. GPT-4 is absolutely massive in scale at 1 trillion parameters and represents the pinnacle of OpenAI's research in large language models, at least at the time of creating this course. ChatGPT is a version of a GPT model specifically fine-tuned for conversational interactions. It's optimized to provide more natural and engaging responses in a chat or dialogue format. It's undergone additional fine-tuning to make it more suitable for chatbot and virtual assistant applications. Getting started with GPT models is pretty simple. OpenAI developed an API to allow you to easily interact with their models and start creating your own custom solutions. So to get started using the API, the first thing we're going to need to do is create an API key from the OpenAI website. So you'll want to go to platform.openai.com and either log into or create your account. Once you're in your account, this is the screen you'll see. You then want to go to your account settings on the top right of the screen and go to View API Keys. You'll see here I already have a few API keys that I've already created, but let's create a new one to show you how it's done. We'll click on Create New Secret Key. You then want to give this secret key a name. In this case, we'll just call it LLMs course. The secret key has now been generated for us, and we need to store this somewhere safe as we won't be able to view it again after this time. So make sure to copy this secret key somewhere safe. To use your API key in your code, you can either drop it straight into the code or you can add it into a config file. Some organizations might also have other ways of hiding these API keys from the code. This is important to make sure your secret key is kept a secret for only you. So I've created this file config.py, and then I'll create my API key and paste the secret key I got from the OpenAI website in this file. In our notebook, we can then import the OpenAI package and the config package. We create our API key, and then we can reference our config file, so we do config.api key. We then want to initialize the OpenAI client, so we run OpenAI.api key equals our API key. And that's it, our API key is now all set up for us to start playing with these models. Let's just make a quick note on pricing. So the different models that OpenAI makes available to us through this API come at different prices. Prices are set per 1,000 tokens. So have a look through this website if you're going to be using these models through the API, and just check the different prices of the different models available. Of course, the more expensive models are the more recent models. Let's now move to our next lesson where we can start interacting with this API. Remember how we talked about the G in GPT standing for generative, because it can generate human-like text? Well, we can test this out by creating a simple function for text generation using a GPT model via the API. So we'll create a function. We'll define our function, generate text, and the input to this function will be our prompt. A prompt is essentially just the text you provide to the model. It can be a sentence for the model to complete, a question to answer, or a set of instructions to follow. And then within our function, we want to call the OpenAI.completion.create function. Within here, we specify the model we want to use. Here we'll be using DaVinci 2, which is one of the base models, but feel free to use whichever model you like here. The prompt for our model will be the prompt for the input of this function, and we also have a few arguments here, such as the maximum number of tokens and the temperature of our output. We'll come on to what these mean in our next lesson. We then want our generate text function to return the response.choices.text.strip to get our output in an appropriate format. Let's now create a prompt to pass to this function. Here we want to try sentence generation, so we'll give the model a prompt of a sentence to complete. Let's give it the phrase once upon a time and see what it comes out with. We then want to create our generated text, and then we can use our generate text function we created with our prompt as the input. We then want to print our prompt alongside the generated text. So we can see the model has given us an output here. Obviously, this isn't a perfect output, but in just a few lines of code, you've been able to interact with the GPT model directly in our notebook. I told you we'd come back to discuss the different options for the function we created. The max tokens and temperature arguments are things we can change in order to get a different outcome from our model. Max tokens refers to the number of tokens we want the model to return. If we set this to a higher number, we'll get back a longer output. Let's experiment with some different values for these arguments. We'll take our generate text function from above, and instead of setting the max tokens within the function itself, we can create it as one of the arguments for our function. We can then create our generated text, but instead of just providing the prompt to our generate text function, we'll provide the prompt and the number of max tokens. Here we'll set it to 5. We've been given once upon a time, this spring, every. Let's now change this to a larger number and see if we can get a full sentence. We'll change the number of max tokens to 20 and print out our generated text. So you can see here the output that's been given is much longer. And you can play around with the number of max tokens depending on what your use case is. You can even just make it a really large number to allow the model to give whatever output that it feels would be relevant. Let's now look at the temperature argument. The temperature controls the randomness of the response, with 0 being less random and 1 being most random. So let's adapt our function, again taking the temperature out of being hard-coded within the function itself, instead an argument we can pass to our function. We'll then generate our text, so we'll give it the prompt, the max number of tokens as 20, and the temperature of 0. Let's compare this to where we give it the same prompt, the same number of max tokens, and a temperature of 1. So you can see with a temperature of 0, the response is quite kind of simple, it's not particularly random, it makes sense. Where the temperature is 1, it will be more random, but because we've limited the number of tokens, it's quite hard to see that. So let's up our number of max tokens to 50. So when we allow the max tokens as 50 and the temperature of 0, we get the following response. Once upon a time, there was a little girl who was born with very special gift. She could see things that others could not. She could see the future and she could see the past. She could see the present and she could see the future. Let's compare this now to where the max tokens is again 50 and the temperature is 1. Here we get the response, once upon a time, I was told everything. I'm guessing this might be in reference to how it's always been a strange position to be in because he doesn't really give much back when anyone does anything for him, but we don't get a perfect view of those. So you can see here the response is a little bit more random, it doesn't make as much sense, it's not quite as clear. So this temperature argument is really interesting to play around with and see what kind of different responses you can get. There are other customization options available, so do check out the documentation. You can also experiment with these on the OpenAI API playground, where you can test out different models and settings. Next, we're going to learn how to create a function that can be given a large chunk of text and summarize it by picking out the keywords. Because the model is able to understand language, it is then able to pick out the most important words and phrases for us. We create our function and provide messages to the model with instructions and examples of how we want the model to respond. There are 3 roles that can be used for messages. The first messages are system messages. These messages provide instructions to the model on what you want it to do and how it should respond and behave. The second type of message is a user message. This is an example of a user input. So in this case, the user input would be the block of text we want to summarize. The third type of message is an assistant message. This is an example of the correct output to the user input. So here we have keywords that have been pulled out from the block of text provided by the user. These assistant messages serve as an example of how the model should respond. So you can see in the code here, we've created a function which we're calling text summarizer. And this function takes our prompt as an input. We use the OpenAI.chatCompletion.create function and specify our model and our messages. This is where we include the system, user, and assistant messages. Our system message we've set to be the following. You will be provided with a block of text, and your task is to extract a list of keywords from it. We then provide an example user message. Here it's a large piece of text about a flying saucer. The next message is the assistant message. So this will be how we want the model to respond in response to the user message above. So you can see here, this assistant message has picked out keywords from the text in the user message, such as flying saucer, guest house, etc. We then give another example in these messages. So we provide another user message, which is another large piece of text about Sri Lanka, and an assistant message, which pulls out the keywords from this text. Here we're just showing the model how we want it to behave in response to certain inputs. The final message we give will be where we provide our prompt. So we set it as a user message, and then the content of this message will be the prompt that we provide. We set the number of temperature and the max tokens, and return the model's response. Let's now give a new prompt to this function. We can print this prompt out for you to read. We'll then create our generated text and reference our text summarizer function and provide it the prompt. When we print this generated text out, we can see that it's the keywords from our piece of text above. In this lesson, we've seen how we're able to provide messages to our model in order to get it to work with different tasks. Not only can we specify a system message to create a keyword text summarizer, we can also use it to create so many different types of outputs. Let's create a function for a chatbot with a twist. Let's create a chatbot that gives a poetic output. We'll define our function as poetic chatbot, and again our input to this function will be our prompt. We again then use the OpenAI.chatCompletion.create function. We specify the model we want to use, and in this case, we'll be using GPT 3.5. We then specify the messages we want to provide to this model that will dictate how it responds and behaves. We'll first create our system message. This provides instructions on the overall purpose of our chatbot. So the content of this system message will be the instruction, "You are a poetic chatbot." We want to include some examples of how the model should respond to different types of prompts. So let's do that with some user and assistant messages. The first user message will be a question, "When was Google founded?" We then want to give the model an example of the response to this. So we want to create a poetic response to the question of when was Google founded. Thankfully, I've already created these example outputs for us. So we can see in our assistant message, the example response does give the answer, the correct answer of when Google was founded, but it does it in a poetic manner. This is exactly how we want our chatbot to behave. Let's give it another example. We'll give a user message with the content, "Which country has the youngest president?" And again, we then need to assume the assistant role to provide the desired response. Again, I've already created this for us, so we can copy this response across. We then specify the final message, which will be from the user, and it will just be the prompt that's provided to our function. We also set the temperature as 1 to allow for some randomness in our poetic responses. And we set our maximum tokens to 256. So now we've created our poetic chatbot function, selected the model we want to use, and provided some instructions and examples of how we expect this model to behave. We can now test this out. So let's give a prompt. We'll give the prompt, "When was cheese first made?" We then want to create our generated text and run our function poetic chatbot with our prompt. Let's then print out this generated text and see the poetic response we received. Perfect, so we can see our model has behaved exactly as we would expect. It's given us a nice poetic response of when cheese was first made. So in this lesson, we've managed to create a chatbot and we've given it a personality. It'll give nice poetic responses to different prompts made by the user. In the last lesson, we were able to code a poetic chatbot. However, the model will only be able to answer questions based on the general knowledge it has from the data it's been trained on. Let's see what happens when we ask a more specific question to this model. So we can create a new prompt that asks, "What is the next course to be uploaded on the 365 Data Science platform?" You can see that the model has given a response, but there's no actual answer in this response. The model isn't able to tell us which course will be uploaded next onto the 365 Data Science platform because it just doesn't have this data available. GPT models have been trained on a lot of data, but this data only goes as far as 2021, so they might not have the most up-to-date information. But there is a solution. Using LangChain, we are able to import our own data and have this read by our language models. Our language models can then reference this when creating a response using the LangChain framework. So let's have a look at what LangChain is and what it can be used for. LangChain is an open source framework that allows developers to combine large language models with external sources of computation and data. Its popularity has soared in 2023, as large language models have evolved and developers are looking for ways to integrate them easily into their applications. LangChain allows you to build end-to-end applications powered by language models. There are going to be use cases where your language model needs to be able to access and understand data related to your business area or some other area of knowledge that it doesn't have currently. Say, for example, you want to use ChatGPT to help you study. We know that this model has some general knowledge, but you can improve on this by giving the language model access to the entire course syllabus you want to learn. You'd then be able to discuss the syllabus with the large language model and learn much more effectively. We can also use an example with business-specific data. Say you want to create a chatbot for your business to assist customers on your website. Unless you're working for a large, well-known corporation, the language model likely won't be aware of your company, or the information could be out of date or need some further context. You can provide your language model with all the information it needs to know about your company so it can effectively help your customers. So, how is LangChain able to ingest our data and have it read by our large language model? The first step is to load in our custom data and break it into chunks, as language models generally have a limit to the amount of text they can deal with at once. We then create numerical embeddings for each chunk of text. This helps us find similar chunks of text within the data, which is useful when our language models are trying to find which parts of text are important when answering a given question. Finally, these embeddings are loaded into a vector store. Vector stores help us find the most similar chunks in the embedding space quickly and efficiently. LangChain can also help you with follow-up actions, such as sending emails based on the response given by your language model. There is so much functionality with this framework, and I encourage you to check out the documentation. For this course, we'll just be focusing on how we can integrate our own data with our large language model. If this is something you're interested in learning more about, check out the dedicated LangChain course on 365 Data Science. The first thing we need to do to work with LangChain is load our custom data and create a LangChain document object. LangChain has a number of different data loaders for different types of inputs. We can use a data loader to read in information from text files, PDFs, HTML, and so much more. There's a great community around LangChain working to build data loaders for a whole range of different inputs. For our use case, we want to read in the latest information from the 365 Data Science website. So we'll want to use a web-based loader to read in information from a website. So we'll specify the URL of our website. In our case, it's 365datascience.com/upcoming courses. We can then use the web-based loader from LangChain to load the information from this web page. We now need to create a LangChain document object. We can create our raw documents and then use loader.load. This will load the text from our URL and convert it into a LangChain document. The next step is to take our data and chunk it up into small pieces. This is necessary in order to make sure we only pass the smallest, most relevant pieces of text to the language model. So we'll create our text splitter and then use the recursive character text splitter. We can then create our documents. So we'll use textsplitter.splitDocuments over our raw documents. This will take the text from our URL and break it up into small pieces for us. Once we have these smaller chunks, we can create our embeddings for each piece of text and store them in a vector store. To create our embeddings, we'll use OpenAI embeddings, and then we need to specify our API key. We can then create our vector store. We'll use from documents, and then we want to store our documents and our embeddings in the vector store. We can now create a memory object. which is necessary to track the inputs and outputs and for the model to hold a conversation. So to create our memory, we use conversation buffer memory. We'll give the memory keys as the chat history, and specify return messages equals true. We can now initialize the conversational retrieval chain. This chain first combines the chat history and the question asked to the model into a standalone question. It then looks up the relevant documents from the retriever and finally passes those documents and the question to a question answering chain to return the correct response. So let's set up our chain. We'll use conversational retrieval chain .from LLM . We then provide our OpenAI API key . And specify the temperature of the response. If you remember, the temperature just controls how random the response is. We then pass our vector store as retriever and pass our memory. And that's it, we're now ready to ask our model questions based on this text we provided from the 365 Data Science website. So we can ask our model again, what is the next course to be uploaded? We then want our result, so we'll use our QA chain and we'll pass our query to our chain. To get our results, we just need to access the answer from the results. And you can see here the model is now able to answer this question. It's correctly identified the next course to be uploaded at the time of creating this course. It's as easy as that to work with LangChain to bring in your own custom data and start to create chains that will power your own large language model applications.